Okay, now that we have done with the comparable interface, let us start talking about trees. First, let us define it. What is a tree? A tree is a data structure that consists of nodes and arcs or links connecting the nodes. So for the first time, if you observe this definition, there is no mention of the word linear, because actually tree is the first data structure we are encountering that is non-linear. All the basic ones that we have seen before, they were linear data structure, but tree is not. The second point to note is that unlike natural trees, for which the root is usually at the bottom and the branches and the leaves are going up, here our trees are depicted in upside down manner, where the root is at the top and the leaves are at the bottom, as you can see in these examples. So these are all examples of trees. We note, for example, that there is a tree here in A, although you cannot see it. Basically what it means is there is a notion of empty tree. A tree can be empty. So tree number A is empty. A tree can also have just a single node, as in B. A tree may also, if you are unlucky, turn out to be very much like a linked list, as we can see in D and E. Or of course you can have more balanced trees, as you can see in F and G and C as well. So these are all examples of trees, with the root at the top and branches going down, and the things at the bottom here are called leaves. We shall describe them in a moment. We shall give a definition for a number of terms. So this is what is meant by a tree. Let us now take some definitions of some terms related to trees. We shall use this tree that you are seeing on the top right as our reference example. First, the root. This obviously is the top node there. A root is defined as a node that has no parent. It only has children but no parent. Then we have what are called leaves for plural, or leaf for single. So leaves are nodes that do not have children. They are at the bottom. For example, this node 2, 12, 20 and 29 are all examples of leaves. We do not mention it in the slide, but the nodes that are neither root or leaves are sometimes called internal nodes. So we have root, internal nodes and leaves. Okay, next definition is a path. In a tree, each node must be reachable from the root through a unique sequence of links or arcs. For example, 29 can be reached from the root by following the path 1320, by following the links 1325, 2531 and 3129. Now this sequence of arcs are what is called a path from the root to the particular node. So the path from the root to 20 will be 13, 25 and 25, 20 and so on. Next is path length, or length of a path. The length of a path basically is the number of links in that path. For example, the path from the root to 29 is of length 1, 2, 3. Yeah, so that's what is meant by a path length. Okay, next definition is level. Level of a node. Level actually is a property of a node rather than property of a tree. So the level of a node is defined as the length of the path from the root to that node plus 1. For example, if you recall, the path length for 29 is 3. So the level of 29 is level 4. 3 plus 1, 4. Actually, it is easier to count the nodes along the path. That will give you the level. So, for example, to reach 29, we have 1 for node 13, 2, 3, 4. So the level of 29 is 4. The level of 12 is 1, 2, 3. Okay, so actually it's more related. Now here the we have to be careful actually, because this definition is not universal. Our book is following the English system, if you like, where level 1 or the first level is considered as level 1. So the root is considered to be at level 1, and then next level will be 2 and so on. Some authors prefer to use the American system, where this is considered as ground level or ground 0. So the root is considered to be level 0, and then level 1 and so on. So do not be surprised if you read in another book where the counting starts from 0. However, for our course, we shall stick to the definition in our book, where the root is considered to be at level 1, and then level 2, level 3, and so on, like that. So that's the definition of a level. Next is height. Height, on the other hand, is a property of the tree itself. Height of a tree, just like you can say height of a building, a higher multi-story building. The height of a non-empty tree is defined as the maximum level of a node in that tree. The maximum level of a node that you can find in that tree. So for our tree here, the height is 4, because the maximum level we can find is 4, the level for 29. So the height of the tree is considered 4. It is obvious, therefore, that the height of an empty tree is 0, because it has no nodes, so it is considered to be of height 0. Okay, now in terms of application of trees, we shall see trees, they have many different applications. Essentially, in any situation where you need to represent data in a hierarchical manner, you will find tree to be useful. Example here is organizational structure of a university, or any organization for that matter. So our university here, for example, JUC, we have 2 campuses, male and female, and within the particular branch we have departments. Within each department we have professors, students, and so on. So this can easily be represented as a tree. Another example we can think of is representing a file system, where you have the drive and then folders and then subfolders and so on until you reach the files inside the folders. So the files will be the leaves, and the drive itself will be the root, and all the folders will be internal node and so on. Yeah, there are many applications of trees. Before we leave trees and start looking at binary trees, a few more definitions. Orderly tree, actually just one more definition. Orderly tree. What do you mean by an orderly tree? An orderly tree is one in which all elements are stored according to some predetermined criteria of ordering. The elements are not just stored randomly, they are stored based on a certain criteria, as you can see in this example. If you can observe, each parent in this tree is less than its children. So 2 is less than 10, 12, and 13. Similarly, if you take 10, it is less than 20, 25, and 29. So this is the ordering criteria for this tree, where the parent is always less than the children. If you organize the elements in a tree in this manner based on a certain criteria of ordering, then the tree is said to be an orderly tree. We shall see, for example, later that binary search tree is an orderly tree, but the order is different than this particular example. It's a different ordering. So the ordering is can vary, and it's not one ordering. All that is required is that there is some order in the way the elements are stored in the tree. If that is the case, then the tree is said to be an orderly tree. Okay, at this point we are going to narrow down to a special type of tree called binary tree. Okay, so what is a binary tree? A binary tree is one whose nodes have 2 children, possibly empty, and each child therefore can be designated with a particular name, left child or right child. Since there are only 2 children maximum, it's easy to name the children, so they are named left and right. So that is what binary, from the word binary meaning 2. A binary tree is where we restrict the number of children to 2. And in fact, as we can see in this example, a node may have even less than the 2. All these examples that we are seeing are valid binary tree, because here it says the node shall have 2 children, but they can be empty. Okay, so actually the 2 is just the maximum number of children a node can have. A node may have 1 child, or it may have no child at all, as in the case of the leaf nodes. This is basically what a binary tree means. It's a tree in which we restrict the number of children to a maximum of 2. Let us well, actually, before we move away from the definition, let us look at a recursive definition for a binary tree. The definition we have just read in the last slide is fine, but actually when we come to implementation of methods, this recursive definition is more useful. It defines a binary tree as either empty or it is made of a single node. That node consists of a data value and 2 references to binary trees. The references are named left and right, each of them pointing to a binary tree. This is why the definition is recursive. It is defining binary tree in terms of binary tree. So when you are looking at this recursive definition, we don't think of a tree as having many nodes. No, it has a single node. However, that node has references to other binary trees, as you can see in this example. So the main tree here, which is enclosed in the purple cycle, has only one node with a key 5. But that node has, in addition to the value 5, it has references to 2 binary trees, which are enclosed in these red cycles. So since this one inside red cycle is a binary tree, it will also have one node containing a value and references to 2 other binary trees, and so on, and the recursion will continue until we reach an empty tree. In this case, for example, the tree in green here has just one node and null references, so it doesn't have 2 subtrees. The subtrees, actually it has, but they are empty. References to 2 empty subtrees. So this is how to define a tree recursively, and as I said, we're going to find this definition very useful when we come to implementing the methods. Okay, now we're going to consider 2 types of binary trees before we again narrow down to another type of tree called binary search tree. First, what is a full binary tree, which is also sometimes called decision tree? A full binary tree is one in which all nodes have either 0 or 2 non-empty children. So each node has either 2 children or it has no children at all. So in a full binary tree, a node is not allowed to have 1 child. Either it has 2 or it has none at all. So the example you are seeing here on the left is an example of a full tree. The root node, for example, has 2 children. This one also has 2 children. Each node is either having 2 children or it is leaf. Leaf means it doesn't have children. So if you have this, it is called a full tree. The second type of binary tree that we are defining here is called complete binary tree. The 2 English words seems to be the same, isn't it? Full and complete. But actually, technically, they are different in terms of trees. Let's see what complete binary tree means. A complete binary tree is one in which every level, except possibly the last, is completely filled, and all nodes are as far left as possible. So every level is filled except possibly the last. There's an exception here. Every level is filled except possibly the last. However, even on that last level, the remaining nodes that are left will be on the right, on the left. So the nodes that are there should be on the left. As you can see in this example, this is an example of a complete tree. Level 1 is full, level 2 is full, level 3 is full, but level 4 is not full. However, the nodes that are there, they are as far left as possible. If this is the case, then the tree is said to be a complete tree. So basically, a complete tree is one that grows top to bottom left right, with no gaps allowed. If we can draw examples, let us draw some example, or an example, to see how to construct a complete binary tree. So obviously when you start, you can only have, I'm not able to do it, unfortunately, but I think you get the point. It grows top to bottom, left to right. So if you have one node here, then the next place you can have another node is to the left, not to the right. If you have to the right, then it means you are leaving a gap on the left, so it's not complete, and so on. So after having the left, then you can have the right, and then you can move to the next level, left, right. So here again, you cannot go down unless you fill that particular level. Only the last level is allowed to be non-complete. And even that, we shouldn't have elements to the right while there are some empty on the left. It has to be top to bottom, left to right. This is the definition of complete binary tree. Now there is one nice property about full trees, which is that there is relationship in full tree between the number of leaf nodes and the number of non-leaf nodes. The number of non-leaf nodes is always less than the number of leaves by 1. Or put another way, the number of leaves is always more than the number of non-leaves by 1. But of course this is specifically for full trees. Let's take an example. If you look at this tree, clearly it is a full tree. There is no node that has one child. All nodes have either 2 children or no children at all. So this relationship is telling us if we count the number of leaves in this particular full tree, it's going to be 1 more than the number of non-leaves. Let's count them and see. The leaves are 1, 2, 3, 4, 5, 6, 7, 8, 9. How about the non-leaves? 1, 2, 3, 4, 5, 6. I think I jumped one here. 7 and 8. Let's do it again. 1, 2, 3, 4, 5, 6, 7, 8. So 8 non-leaves and 9 leaves. This is what this formula is saying, that for a non-empty full tree, the number of leaves, if you call it M, is greater than the number of non-leaves or non-terminal nodes, call it K, and the relationship is that M is K plus 1. If you add 1 to the number of non-leaves, then they will be equal to the number of leaves. This second figure is showing us that if you add more nodes, provided the tree remain full, then the formula remain correct. So suppose, for example, we change one of the leaf nodes, this one, and make it to have children, 2 children. Will the formula still be correct? Obviously the non-leaves have increased by 1. So if they were 8, now they are 9. How about the leaves? Are they also increasing by only 1? Of course yes, because although we added 2 leaves, we have removed 1, because this was a leaf before and now we change it to non-leaf. So effectively we have added only 1 leaf. This is what this formula is saying. We subtracted 1 from the non-leaves and added 2 leaves. So the formula still remains. The number of leaves is 1 more than the number of non-leaves. This is basically where we're gonna stop about binary tree and start talking about our main target, which is binary search tree. Binary search tree is the one actually that is our target, is the one we are going to study in detail, all its basic operations, and in fact it's the one that we are going to also implement as Java code. So what is binary search tree, which sometimes is shortened as BST? A binary search tree is a binary tree, of course, but one that satisfies the following ordering property: that for each node number n of the tree, all values stored in its left subtree are less than the key stored in node n, the value v stored in node n, and all values stored in its right subtree are greater than the value v that is stored in n. Okay, so basically a binary search tree is an orderly tree in which the ordering criteria is as specified here. It is better to understand this with an example. So let us see an example. Consider the tree in figure C here. If you take the root, it has a value 13. So according to this definition, if this is a binary search tree, then all the elements in the left subtree of 13 should be less than 13, and all the values in the right subtree of 13 should be greater than 13. And this should go throughout the tree. It's not only for the root, any node. For example, if you take 25, its left is 20, so 20 is less than 25. And its right contains 29 and 31, both of which are greater than 25, and so on. So if you have this ordering throughout the tree, then the tree is said to be a binary search tree. Obviously the name BST or searching tree is coming from the fact that it is now easy to search for elements in this tree. It's going to be very similar to the binary search that you already learned from programming 2. Okay, for example, if you are looking for 29, you just compare with the root here. 29 is greater than 13, so you don't waste your time looking for 29 on the left. Just go to the right. And similarly, we will talk about searching in a moment, but basically this is where the name comes from the fact that it is easy to search in a binary search tree. Now the tree, of course, the element do not have to be numbers. They could be letters, as you can see in figure A, or words, or in fact any object. The only criteria is the element should be ordered according to this ordering criteria. In the case of letters and words, the ordering will be based on the alphabetical listing of the letters, or the dictionary ordering of the words, and so on. So this is what is a binary search tree. So let us try and discuss about its implementation. We're going to do this implementation gradually, because for each method we will try to explain the operation first manually with examples before we try to see how it can be implemented in Java code. Now, as we have seen with other data structures, there's always two different ways that you can follow in implementing a data structure. You can use arrays, or you can use a link structure. And since we're going to be implementing using link structure, I will actually skip the explanation about arrays implementation. So let us move right to the link structure implementation of binary search tree. And as we did with a doubly linked list and singly linked list as well, we're going to start by looking at the node class, and then we look at the binary search tree class itself. So this is the node class for the binary search tree. Probably I will go to NetBeans to discuss this a little bit more so that I can emphasize on some of the important things to note in this class. So I have here the BST class, and as an inner class we have the BST node class. Now if you observe this class heading for the BST, is very similar to that of DLL node, but there is one big difference. Let's look at the DLL node class. The DLL simply says private class DLL node of generic type T and stop there. But here in BST it says BST node, private class BST node of generic type T that extends comparable T. This is the difference, or this is the addition. The question is, what does this mean? We know, of course, that an interface, a class cannot extend an interface. So what does this statement mean? T extends comparable T. Basically what this means is our generic type T should not be just any type. We are putting some restriction here. For our type to be stored in a doubly linked and in a BST node, it must be comparable. This is what this statement actually means. It must be a type that implements comparable. Notice that although the word extend is used here, actually what is meant is that the type T that you're gonna use for this to store in this node class must be a comparable type, must be a type that implements the comparable interface. This is basically the restriction, and this restriction obviously is because of the fact that we need to be able to compare the data element that we're going to store in a BST, not only for equality but also for less than or greater than. Otherwise, how do we know when to put an element to the left and when to put it on the right? So this is why the T, there's a restriction here. It's not just any type T, but a type T that is comparable. Other than this, the rest is very similar to the definition we had for the DLL node. We have an info variable here, but this time it is called key. So we have key of type T, and we have two references of type BST node. But instead of prev and next, this time they are called left and right. So a node has three data values or three references, the key and references to two other nodes, which are left and right. The constructor here is simply initializing the three variables with the three arguments that it receives. The element is going to be used to initialize the key, LT is used to initialize the left, and similarly for the RT. The other two constructors I believe are obvious. This is if you have only the key, then you're gonna call this constructor supplying null for the left and right. So this can be used, for example, to create a leaf node, a node that has just the info with no subtrees. And the default constructor is setting everything to null. So this is our node class. No methods, just the variables and the constructors. Let us go back to the presentation. After the node class, we now have the binary search tree class. So again, the main point to note is the T has a restriction this time. It is not just any T, but it is a T that is comparable. Other than that, it's the same like DLL. The BST is also iterable, so we put implements iterable. In terms of variable, this time there is only one variable called the root. So root of type node, of type BST node. In DLL, if you recall, we have two references, head and tail, but this time it's only one, which is called root. The constructor does nothing because there is nothing to do actually, just initializing root to null. We can also explain these easy methods. Clear is to empty the tree simply by setting root to be equal to null. Its empty method will return true if root is null and false otherwise. And the last method here, called visit, will receive a reference to a node and simply print the key of that node, print p.key. We're going to use this method a lot when we come to traversal. So basically we give it a node and it will print the key of that node. This is the visit method. For the rest of the method, I will just give you the heading here. But as I said, before we look at each of them in detail, we will first learn how to do the operation first manually with examples, and then we look at the code. So these are the methods we expect to see in the BST class. We can categorize them into about 3 or 5 groups. First, there is the searching methods. There is search, which will take an element and return a similar element in the tree. And there is a Boolean version of it called isInTree, which will take an element and just tell you whether it is there or not. Then there is a group of methods for traversal. All these methods are for traversal. There are about 4 of them: breadth first, pre-order, in order, and post order. As we're going to see, in trees there are many different ways you can traverse it. Unlike doubly linked list, where there is only 2 ways, either forward or backward, here there are many different ways you can traverse a tree. The next group is just one method for insertion, and then another one for deletion. And the last method here is the iterator method, because we said that the tree is iterable, so we must implement the iterator method. And as we recall, to implement an iterator method, we need an inner class that implements iterator. So that inner class, we call it BST iterator. So these are the main methods that we're going to find in BST. What we're going to do next is to take each of these operations one by one, explain it in detail with an example before we look at the method. Starting with searching. Searching, I think I already explained it earlier. This is one of the main advantages of binary search tree compared to linked list. It allows you to search very fast. All you have to do is start from the root, compare your target against the root. If your target is smaller, then you know you only need to search on the left. If it is greater, then you only search on the right. And then you repeat the process. you consider this as a new tree. So compare your target against its root and decide to go left or right. So if you are looking for 29, for example, 29 is greater than 13, so we're going to go to the right. 29 is greater than 25, so we're going to go to the right again. But 29 is less than 31, so we're going to go to the left. And this time 29 is equal to our target. I mean the root here is equal to our target, so the searching will stop. What about if what you are looking for doesn't exist? Let's say we are looking for 11. So we start from the root. 11 is less than 13, so we're going to go left. But 11 is greater than 10, so we go right. Now 11 is less than 12, but there is no left to go to. Left is empty. What does this mean? It means 11 doesn't exist in a tree. So either we reach a target or we reach an empty. If we reach an empty tree, it means the target doesn't exist. This is basically how to search in a binary search tree. And you will be surprised to see that in fact the Java code is doing exactly that, because it is recursive. Remember, recursive methods usually are more intuitive. They relate more to the problem than iterative one. Let us look at the main method here, which is the recursive method. So the search method will receive two inputs: target element and reference to the tree in which we're going to search, called P. So first what it will do is it will check, is P equal to null? Because if P is null, it means we have reached one of the two possibilities that we mentioned here. Either we reach an empty or we reach a target. So if we reach null, it means the key doesn't exist, the target doesn't exist, and therefore just return null. But if the P is not null, the tree is not null, the next thing we do is to check how does our target compare to P.key. If you do compare to and you get less than 0, it means your target is smaller than P.key. So all you have to do is repeat the search, but this time on the left subtree. And recursion allows us to do this by simply making a recursive call. It says return the result of searching of element on what? P.left. On the other hand, if your target compared to P.key is positive, it means your target is greater than P.key. So just repeat the search on the right subtree. Okay, and so on. And finally, if you see else, so it is not null, target is not less than, target is not greater. What does that mean? It means target is equal to P.key. Therefore, just return P.key. This is basically the search method. It's very compact and very intuitive, very much related to the searching as we do it on a BST. Now the other method here is an auxiliary method, because actually we need to give a starting value of P, and usually that is the root. So, and we don't want the user to have to be the one to give that starting value. The user should just provide his target, take my target, and return to me a similar element if it exists in the tree. So here in this auxiliary, we now call, this is why this is public, because this is one we expect the user to use, and this one can be either protected or private. So in this, we just call this one, sending the same element that we receive, but sending root as the initial value for p. Yeah, this is the search method. I think probably we can stop here and complete the rest of the lecture in another remaining part.